Assalamualaikum. Today I'm going to be presenting our high-performance computing project titled Linear Discriminant Analysis and Scatter Matrices. Here's an overview of what we'll be discussing. We first talk about our dataset, the theoretical basis of LDA, and then our parallelization strategies using OpenMP and CUDA. And we finally discuss the results of applying some machine learning. We benchmark our work using the UCA human activity dataset, which contains phone sensor data collected from people wearing Samsung phones on their waist while doing 6 different activities, meaning our dataset has 6 classes or labels, 561 different variables or dimensions, and 10K entries or rows. In order to explain the theoretical intuition, I'm going to resort to using a simpler example that can be more easily visualized. I'm going to use the following dataset that contains 3 classes, 2 variables, so it's 2D and only 20 entries. This graph shows the dataset. Now the goal of LDA is to simply minimize the distance between the points of each class while maximizing the distances between the classes themselves. So we'd ideally want the points of the same color to be closer together, and we want each cluster of a certain color to be the farthest possible from the other ones. First off, we find the center point or the mean of each class. Then we calculate the scatter of each class through calculating the distances between each point of the class and its mean. Programmatically, we do this through accumulating the SW, or the scatter within matrix. After that, we use the means to find the central point of the dataset and calculate the scatter between classes through calculating the distances between the means and the central point. This is the equivalent to programmatically accumulating the SB, or scatter between classes matrix. After calculating both scatter matrices, they are simply plugged into the LDA formula to find a new plane which minimizes the scatter within classes and maximizes the scatter between them. It is worth noting that the dimensions of the result of LDA equal the number of classes minus 1. So here, since we have 3 classes, we get a 2D plane. In our main dataset, since we have 6 classes, we get a 5D plane. Now, from an HPC perspective, the bottleneck while implementing this is calculating the SW, or the scatter within class matrix, because we need to take every data point across multiple dimensions into account. The SP's loop only contains a number of iterations equal to the number of classes, so it's negligible. Now on to the parallelization strategies. We obviously have a serial version to compare against. The OpenMP version uses the pragma1p parallel 4 with the minus reduction operation, so each thread gets a portion of the dataset, while the GPU version tries to do all the calculations simultaneously using tiled memory and atomic adds. We now show our benchmarking results. First off, we have this boilerplate of imports that ensures that the C code, which is how we implemented our LDA algorithm, is compiled and the dataset is loaded successfully. And we test that the algorithm is implemented correctly, etc., etc. The part we care about here is the speed up benchmark, which is this one. We notice that the speed up gets better as we add threads and reaches its peak at 4 threads, and then it starts to decline. The reason behind this is that the machine we tested on likely has 4 cores, 4 physical cores, so scheduling more threads or logical threads will only add scheduling overhead and won't help it better, while using just 4 threads ensures that they run all simultaneously, each on 1 core. This is also reflected in the all clock time, as it's the minimum it can be when using 4 threads. And when it comes to the GPU implementation with CUDA, we do the same boilerplate. For disclosure, this was ran on another machine, but luckily for us, the speed up metric is independent from hardware, and so we can use it. The main point here is that the GPU implementation is actually slower than the OpenMP implementation, and that is because of the overhead from transferring data to and from the GPU memory. And we've also plotted the results after splitting the dataset. As we mentioned, the result in projection is 5D. Here we're only printing the first and the second dimension. As we can see, we get the same result from each of the three implementations. And we then apply some machine learning, specifically the KNN algorithm, and we see that three versions perform all the same. We get the exact same accuracy since they're applying the exact same logic. And it's also worth mentioning that our algorithm actually performs slightly better than the sklearn implementation. So that's just fun. Otherwise, that would be all. Thank you for auditing and have a good rest of your day.